Alright guys, this video is going to go over electronic configurations. You will need your periodic table, so make sure you have that out along with your note sheet that says Notes Electronic Configurations. So giving you like 30 seconds to get those things out. Alright, here we go. Okay, so you're going to see some vocabulary that you've seen before. Just rewrite it again. The more you see it, the faster it stays in your mind. So a valence electron, or valence electrons, are the electrons in the outer energy level, the very last ring or shell on an atom, the very, very last one. So for example, in these pictures, there's one ring here, it's the very last one, it has one valence electron. Here there would be two, and here there would be three. A Lewis dot diagram is used to show the number of valence electrons in an element. So you have all of these on your sheet. I want you to go ahead and draw in the correct number of dots. They each represent how many valence electrons something has in the last energy level of that atom. Okay, right here I want to point out that there's a very specific way we draw these in, and you're following the numbers. So we always draw the first electron on the right hand side at the top. Okay, so right here. Then here's where the second one goes, then third, fourth, fifth, sixth, seventh, and then the last one would be the eighth. It must be drawn in that order. So remember that electrons do not orbit the nucleus however they feel like. They are organized into energy levels. So where are electrons found? They're in energy levels around the nucleus. And you can have multiple energy levels. Let's look at 3 for right now. So we have our first energy level, our second energy level, and our third energy level. Remember, the nucleus is in the middle, and then we just draw the energy levels as circles. If there is a dot on the energy level, those dots represent electrons. Rows on the periodic table are known as periods. All of the elements in a period have the same number of energy levels. So let's look at this our little periodic table that we have here. This would be period 1, here would be period 2, here would be period 3. So if we start with just 1, it means that both hydrogen and helium will only have one circle, one energy level around their nucleus. Here is period 2. It means that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon will all have 2 circles or 2 energy levels around their nucleus. So each energy level is broken down into 4 sublevels. So again, there are 4 sublevels that you need to know because each energy level is broken down into these 4. The higher the energy level, the more sublevels it has. So the sublevels are S, P, D, and F. Again, the 4 sublevels are S, P, D, and F. S holds 2 electron, so it's a very small sublevel. P holds 6, D holds 10, and F holds up to 14. Okay? So again, S can hold up to 2, P up to 6, D up to 10, and F up to 14. Excuse me. Each energy level has an additional sublevel from the energy level before. So I know that sounds confusing, so here's how you need to think about it. The first energy level only has an S sublevel. The second energy level has S and P sublevels. The third energy level has S, P, and D sublevels. So what do you think the fourth has? Yes, I'm waiting for you to answer me. Hopefully you said the fourth energy level will have S, P, D, and F. Okay, so let's do it again. First energy level only has S. The second has S and P. The third has S, P, and D. And the fourth will have S, P, D, and F. Don't forget, S holds 2. S plus P holds 8 because 2 plus 6 is 8. S plus D, so S plus P plus D would be 18 because that's 2 plus 6 plus 10 equals 18. And S plus P plus D plus F would be 32 because that would be 2 plus 6 plus 10 plus 14 equals 32. Don't forget that the arrangement of the periodic table is based on the sublevels, okay? And that's why the periodic table kind of has that funny shape. So everything that's highlighted in blue is going to have an S sublevel. Everything that's highlighted in P is going to have up to a P sublevel. So it'll have an S plus a P. Everything that's highlighted in D is going to have up to a D sublevel. Everything that's highlighted in green is going to have up to a F sublevel. So S, P, D, and F. Now you're probably wondering, why do we care what levels and how many electrons and all of that? Well, remember I told you, I think 2 videos ago, that chemical reactions depend on how many valence electrons you have. And if you're going to give those away, or if you're going to take them from another atom, or if you're going to share them with another atom. So that's why you need to learn the electronic configuration, because you need to know how many electrons an atom has, and if you know that, you'll know how that atom is going to behave. So the way we show electronic arrangement in energy levels is called electron configuration. So again, the way scientists show the arrangement of electrons in energy levels and sublevels is called electron configuration. And the electron configuration of an element will not have to be memorized. You can use your periodic table to help you remember it. And I'm going to show you how in a few seconds. Okay, so you probably would have noticed on the periodic table that I've had up, that we have like a number and a letter and then maybe a subscript. So let me show you this example. This is 1s2, 2s2. Okay, so 1s2, 2s2 is the element beryllium, which is right here on the periodic table. Excuse me. So let's talk about what these numbers and letters mean. So the coefficient, which is that big number, the one I have underlined, represents the energy level that that element is in. Remember, there are 4 energy levels. So 1s2, the 1 tells me that this element is in energy level number 1. Okay? The second letter represents sorry, yeah, the letter, not the second letter, but the letter represents the sublevel. So remember there are 4 sublevels, S, P, D, and F. So 1s, the S tells me that this element has an S suborbital, a subenergy level of S. Then the superscript 2 tells me how many electrons is in that sublevel. So in my 1s sublevel, I have 2 electrons. In my 2s sublevel, I have 2 electrons. Okay, so that's what these numbers and letters mean. So I'm going to give you like 15 seconds or so to write that down. So let's use phosphorus as an example. Here is phosphorus right here on this periodic table. We know this is period 1, this is period 2, and this is period 3. So it looks like we're in period 3. So let's see if we can figure our way through this. So we're not in 1 or 2, so that means we filled up the first 2 energy levels. We know that over here, this is the S sublevel, and this is the P sublevel, and this is the D sublevel, and this is the F sublevel. So phosphorus, which is right here, yeah, phosphorus is in that P sublevel. So we know we filled energy levels 1 and 2, and we know we're in the P sublevel. Now, if we count how many electrons in we are, or not electrons, but how many atoms in we are, sorry, we're 1, 2, 3. We're the third atom in on that third row. So the way we would write the electronic configuration would be 1s2, 2s2, because remember the s's can only hold 2, 2p6, 3s2, 3p3. Now you're probably thinking, well, why didn't we put all the s's together and all the p's together? I'll tell you why in a second. So I think there's a place for you to write this down. Hopefully you are writing it down. Here we go. So why didn't we write all the s's and the p's together? Well, it's because we have to fill the sublevels in a specific way. And certain sublevels represent certain energy levels. So here's the rule. Here's how it goes. 1s2 represents energy level number 1. 2s2 and 2p6 represent energy level number 2. 3s2 and 3p3 represent energy level number 3. But we didn't fill our 3p sublevel, which is why we only have 3 here. Technically it can hold 6, but because we've run out of electrons, we only have 3. So that's why we don't write them together, because 1s, that's energy level 1. 2s and 2p, that's energy level number 2. 3s and 3p, that's energy level number 3. That's how it goes. Okay, so let's see if we can figure out which elements have the following electronic configuration. So the first one says 1s2, 2s2, 2p6, 3s1. So let's go through the periodic table and see if we can figure it out. Now, hydrogen would be 1s1. We know this one has at least 1s2, so it can't be hydrogen. It can't be helium because helium is 1s2. We go all the way up to 3s1, so we're just pretty much crossing out until we get to 3s1. 2s2 means that we can't be lithium because lithium is 2s1. We can't be beryllium because we go up to 3s1. 2p6 would mean that we are not boron or carbon or nitrogen or oxygen or fluorine or neon because we go up to 3s1. Sodium is in 3s and it is the first element, so sodium would be our answer for this question. See if I can get rid of. Okay, so let's see if I can get rid of this box. Okay, so it is sodium. Let's look at the next one. Let me erase these. Oh, come on. Okay, I'll just do it in a different color. So the next one says 1s2, 2s2, and 2p5. So hydrogen is 1s1, so it can't be that. Helium is 1s2, so it can't be that because we're going up to 2p5. Lithium is 2s1, beryllium is 2s2, so 2p5 is the magic one. So let's see, boron is 2p1, carbon is 2p2, nitrogen 2p3, oxygen 2p4, fluorine is 2p5, so that would be the right answer for this one. All right, and fluorine is the right answer. So go ahead and write those down, and then we'll do some more practice in a little bit. This is one of those things that the more you practice it, the easier it becomes for you to do it. So the sublevels are not filled in order. I wish I could tell you we fill all the S's, then we fill all the P's, then we fill all of the D's, then we fill all of the F's, but that's not true. And the reason they're not filled in order is because it depends on energy. So here's how you have to think about it. Energy increases as you go down the period. So lots of energy is going to be down here. You're going to have a little bit of energy here. So because of the difference in energy, it is always going to be easier to make a new S sublevel than it is to make like a P sublevel or sometimes a D sublevel. So that's why you're going to find the S's are filled kind of all over the place. So this little diagram right here, you really need to know this diagram. It's very, very important because it tells you the order in which the energy levels are filled. You just have to follow the arrows. So I'm going to switch to my laser and follow me. So 1s is always filled first. After 1s, 2s is filled. After 2s, 2p is filled, and then 3s is filled. So it's 1s, 2s, 2p, 3s. After 3s, 3p is filled, and then 4s is filled. After 4s, 3d is filled because it takes so much energy to make the d's that we try to fill other things first. So then it's 3d. After 3d is 4p. After 4p is 5s. After 5s is 4d. After 4d is 5p. After 5p, 6s. After 6s, 4f. After 4f, 5d. After 5d, 6p. After 6p, 7s. After 7s is 5f. After 5f is 6d. After 6d is 7p. And that's how we fill them. For the most part, you're not going to have to ever worry about the ones all the way down here, but you still need to know how they're filled. So you're going to see this little diagram show up a lot. So an important fact to remember is that the 4s sublevel is filled before the 3d sublevel. 5s fills before 4d. And it happens this way because it takes a lot of energy, it takes a lot less energy, to make a new S sublevel than it does to make a D sublevel. Okay, so let's try again with two more elements. Notice that these are way bigger. So we're just going to do what we did before. We're going to go through and cross out the ones that it can't be. Remember, we're trying in this first element, we are trying to get to 3d6. So that's the one we're looking for. So we know it's not going to be the S's, any of the 1s's. It can't be any of the 2s's. It can't be any of the 2p's because we're getting all the way to 3d. It can't be 3s. It can't be 3p. Can't be any elements there. It can't be 4s. Now we're in the D's. Remember, the D's are in this middle section of your periodic table. And we're looking specifically for D6, so for the element that is D6. So strontium is going to be D1, titanium is going to be D2, vanadium D3, chromium D4, manganese is D5, and iron is D6. So this would be our answer right here. Let's see if we're right. If I can ever figure out how to get... Okay, so let's see if we're right. And we are. The correct answer is iron. So let's see if we can do the other ones. I wish it would let me erase. I don't know why it's not letting me erase. No. Okay, sorry guys, it's just not working with me today, but we'll just do the best we can. Okay, so this time we are trying to get to 3D2. So same process, I'm just going to switch color. So we know it's not going to be any of our 1S's, or our 2S's, or our 2P's. It can't be any of the 3S's or the 3P's, because we're trying to get all the way to D, so we have to be in that yellow section. It can't be the 4S's either. So now we're in the D section. We're looking for the second element in the D section. So again, strontium is D1 and titanium is D2. So the right answer would be titanium. All right, let's see if we got it right. Yes, titanium is the right answer. Good job. So there's another way that we can write out electronic configuration that makes it a little bit shorter, and it's what we call noble gas notation. So what we do is we use the noble gases, and don't forget the noble gases are the ones on the very end. They're in group 18, and we use them because they're at the end of the row. So if they're at the end of the row, it means that everything up to that noble gas is completely full. So if we used helium, for example, it tells us that 1s1 is already, or 1s is already full. If we use neon, we know that the 1s's are full, the 2s's are full, and the 2p's all the way up to neon are full as well. So it just helps to make everything shorter and a little bit easier to write. So here's an example for germanium, and we have argon and 4s2, 3d10, and 4p2. So let's see if we can figure it out. Argon is right here, so we know that everything else is full. After argon, we have 4s2. So that's this one and this one. Now we're going up to 4p2, so we can skip all the way to the p section. And we're going to the second place, so that's 1 and 2, which would be germanium. Okay, so everything else is just like practice. And this specifically is practice just using the noble gas notation. So if you see the noble gas, you know that everything in front of this noble gas is full. You're just looking at what's left to find your element. So go ahead and copy these down. Okay, so now you should be able to find an element on the periodic table and be able to write out its electronic configuration. We will do some practice of this in class. Okay, so here's the very last practice problem. It says, which of the following is the element configuration of cobalt? So step 1 is we just kind of go through. Find cobalt, which is right here. It's in the 3D section. So anything that doesn't end in 3D is automatically out. So there goes C and there goes B. Those are out because they don't end in 3D, sorry. And it is the 7th element in 3D. So we're looking for something that ends in 3D7, which would be B. All right, and then here are just some more practice problems. You can go ahead and copy those down.